Hello, मेरे प्यारे बच्चों, and welcome back. Exams are just around the corner, and I know, the tension is building up. But please, don't you worry one bit. Your favorite tutor is here with a super quick, super easy revision explainer for you. Today, we're gonna absolutely master mechanical properties of solids and make sure you get full marks from this chapter. Are you ready? Chalo, let's get started.
Okay, so let's just jump right in. You know when you see one of those huge construction cranes lifting a super heavy car, and you look at that thin steel rope and just think, how is that not snapping? It seems totally impossible, right? Well, the secret is all in the amazing physics of solids, and that's exactly what we're going to figure out today.
So our first section is solids have feelings too. I know, it sounds a bit funny, but honestly, it's kind of true. You and I, we tend to think of a steel rod or a wall as being completely rigid, right? Like it doesn't move at all. But actually, in the real world, nothing is perfectly rigid. When you push or pull on solids, they stretch, they compress, they bend, they react. And that's what we're going to study. Now, to understand this entire chapter, you just need to become best friends with these two concepts, stress and strain. Trust me, it's very simple, Beta. Think of it like this. Stress is the internal gussa, the anger or pressure a material feels when you apply a force to it. It's that force from the inside, fighting back, saying, hey, leave my shape alone. And strain? Well, strain is simply the reaction. It's how much the material's shape or size actually changes because of that stress. Just remember this one thing. Stress is the cause, and strain is the effect. Simple as that.
So, we have a few different types of stress. First on our list is tensile stress. The easiest way to think about this is to imagine you're stretching a rubber band. The force you're applying is trying to pull all its molecules apart. That internal gussa inside the rubber band that's fighting back against your pull, that's tensile stress. So it's the stress that happens whenever you try to make something longer.
Next up, we have shearing stress. Now, this one is a little different. Imagine you have a really thick book, maybe your physics textbook. Okay, now put it on the table. Place your hand flat on the top cover and push it sideways. See how the top pages slide a bit over the bottom ones? That movement, that is shearing. Shearing stress happens when you try to slide the layers of a material past each other.
And our third type is hydraulic stress. For this one, I want you to picture a diver who's going deep, deep, deep into the ocean. The water is pressing in on him from every single direction, right? From the top, from the bottom, from the sides, everywhere. That is hydraulic stress. It's the stress a body feels when it's being squashed uniformly from all directions, which usually causes its volume to get a little smaller.
All right, great job. Now that we know our main characters, stress and strain, let's move on to section 2. We're going to talk about a very simple but really, really important rule called Hooke's law. This, my dear students, this is the golden rule you absolutely must remember for your exams. A brilliant scientist named Robert Hooke figured out that for most materials, as long as you don't stretch them too much, stress is directly proportional to strain. It's so simple. The more gussa you create, the more stress, the more reaction you're going to get, the more strain. This simple, direct relationship is the absolute heart of this whole topic. So, you know in math, right, if two things are directly proportional, there has to be a constant that connects them. Well, that constant, which we call K here, is called the modulus of elasticity. Just look at the formula. Stress equals K multiplied by strain. You can think of K as the material's stubbornness factor. A material with a high modulus, like steel, is very, very stubborn. It needs a huge amount of stress to show even a tiny bit of strain. It really, really resists being deformed. Okay, you're all doing so well. Now for what I think is the most interesting part. We're going to look at a graph. I know, graphs can sometimes feel a bit boring, but trust me, this one is like watching a full-on Bollywood movie with lots of drama. So let's look at the life story of a material in section 3. Take a look at this. This graph shows the entire life of a metal wire as it's being stretched. See that straight line from O to A? That's the happy, disciplined part of its life. It's following Hooke's law perfectly. This is the elastic region. If you let it go, it bounces right back to its original shape. But if you pull it past point B, the elastic limit, oh, the drama begins. It enters the plastic region. From this point on, it's permanently deformed, kind of like stretched out chewing gum. Keep pulling, and it reaches its maximum strength at point D, and then snap, at point E, it fractures. The end of our hero wire story. So sad, no?
Now, using that little story, we can easily understand a very common exam question. What's the difference between ductile and brittle materials? It's really simple. Ductile materials, like copper wire, they have a long, dramatic plastic journey. They stretch and stretch and stretch a lot before they finally break. That's why we can make thin wires from them. But brittle materials, like a piece of glass or even a biscuit, they aren't so dramatic. They show almost no plastic deformation. They just snap, all of a sudden with no warning. For them, that fracture point E is very, very close to the elastic limit B. Excellent! You are all doing so well. Now, remember we talked about 3 types of stress a little while ago? Well, guess what? We have a specialist modulus for each one. I like to think of them as a team of superheroes. Let's meet the 3 musketeers of modulus in section 4. First up, we have the most famous one, Young's modulus, which we write as a capital Y. This musketeer is the specialist for stretching and compressing, what we technically call longitudinal stress. It basically tells you how stubborn a material is when you try to change its length. So anytime an exam question talks about wires or rods or pillars in a building, Young's modulus is the hero you need to call.
Our second musketeer is the shear modulus, or G. This is the specialist for bending and twisting, for shearing stress. Remember our book example? Well, shear modulus tells you how much a material resists a change in its shape when you try to slide its layers. So it's super important for things like twisting a metal sheet or for the base of a building that has to resist the shaking of an earthquake.
And the third musketeer is bulk modulus, B. This is our specialist for squeezing, for hydraulic stress. It tells you how much a material resists being compressed or having its total volume reduced. Now, this is really important for liquids and gases, of course, but it also applies to solids when they're under uniform pressure from all sides, just like our diver at the bottom of the ocean.
Okay, Butcho, the theory part is officially done. You've learned all the concepts. Now for the most important part, how to use all this to solve real-life problems, and more importantly, how to score full marks in your exam. Let's get practical in section 5.
Let's just look at some real data from your textbook. See the Young's modulus for steel? It's 200. Now compare that to aluminum, which is only 70, and copper at 110. What does this tell us? It proves that steel is much, much stiffer, much more stubborn than aluminum or copper. It means you need a way, way bigger force to stretch a steel wire by the same amount as a copper one. All right, it's time for a trick question. This one confuses so many students year after year, but not you. Are you ready? Okay, which is more elastic, steel or rubber? Now, in everyday language, we'd all say rubber because it stretches so much. But in physics, well, the answer is going to surprise you. The answer is steel. Yes, I'm serious. It sounds crazy, but it's true. You see, in physics, elasticity isn't about how much something can stretch. It's about how strongly it resists being deformed in the first place and how perfectly it returns to its original shape. Since steel has a much, much higher Young's modulus, it fights deformation much more strongly and it bounces back perfectly. So, in the language of physics, steel is more elastic than rubber. Please remember this for your exam. Okay, get your paper and pen ready. Here is a PACA guaranteed 3-mark question taken right from your textbook examples. We have a steel rod with a radius of 10 millimeters and a length of 1 meter. It's being stretched by 100 kilonewton force. We need to calculate the stress and the strain. The value for Young's modulus, Y, is given. Don't panic when you see the big numbers. We're going to solve this step by step. It's super easy, you'll see. Let's just break it down together. Step 1. Always calculate the cross-sectional area first. The rod is circular, so the area is pi times r squared. But be very careful with the units. You have to convert the millimeters to meters first. Step 2. Calculate the stress. We know the formula. Stress is simply force divided by area. That's easy. And finally, step 3. To find the strain, we just rearrange Hooke's law. We know stress equals y times strain, so strain equals stress divided by y. You just put in the values, do the calculation, and there you have it. The stress is 3.18 times 10 to the power of 8, and the strain is 0.16%. You do this, you get full marks guaranteed. Now, let's go all the way back to our first question about the crane and engineering marvels. You've probably seen this I shape everywhere, right? In bridges, in construction sites. It's called an I-beam, and it's a totally brilliant engineering trick.
This specific shape gives the maximum possible resistance to bending, which is all about Young's modulus, while using the least amount of material. It makes things super strong without being too heavy or too expensive. How cool is that?
So you see, physics isn't just something in your textbook. It is literally all around you. So right now, just for a second, I want you to look around. Look at the building you're in, the bridge you crossed to come to school, even the chair that you're sitting on right now. Can you now see the invisible forces of stress and strain, these elastic properties that are holding your entire world together? It's amazing when you think about it. Okay, my dear students, that's all for this chapter. Just revise these points, and I promise you, you will do fantastically. All the very best for your exams.